Welcome, STAT students, to the lecture for week 4. So far in the course, we've looked at descriptive statistics in a number of ways. We saw how organizing data into a frequency distribution allowed us to see patterns in the data. We were able to see when data was compressed or spread out. We could also assess whether there were any particular data points that dominated the data set. Also, we could organize our data into frequency histograms and polygons to see the shape of distributions, especially in terms of whether they were shaped as normal distributions or skewed in a positive or negative direction. And we talked about the ramifications of each of these shapes in our discussion of both floor and ceiling effects. We then turned our attention to describing data with numbers, and we started with measures of central tendency, by coming up with numbers that best typified the dataset. And we explored 3 measures, mean, median, and mode, and discovered that though each measure provides a number that reflects a typical value in the dataset, there are situations where these 3 measures can provide dramatically different results. It's therefore the role of the statistician to carefully evaluate and select the measure that best captures the most typical value in the data. In today's class, we're going to learn that measures of central tendency only provides a partial numeric description of the data set. A complete description also includes a measure of dispersion or variability as well. So let me illustrate this with something that really happened to us. Last winter we were getting really tired of the super cold winter weather, so we decided to plan a trip to a warm weather destination during the Christmas break. Our first step, of course, was to visit our local friendly travel agent who also happens to have, of course, an advanced degree in statistics. She presented us with 2 vacation destinations for our consideration, and being a good statistician, of course, she presented us with frequency information about the temperatures of both destinations as you see on the display in front of you. Notice that both vacation spots have the same average temperature, 75 degrees. Where they differ, of course, is in the spread or variability of the temperatures. In vacation spot A, there's a narrow variability of temperatures. It looks to range between, say, 65 and 85 degrees. With vacation spot B, though it looks like it gets quite a bit warmer than A, it also has a good chance of getting much colder as well. If you wanted a warm weather vacation destination with minimal risk of cold weather, which of these 2 vacation spots would you select? Most people would have selected vacation spot A. So just knowing average temperature, a measure of central tendency, only gives you part of the information you need to make an informed decision. Understanding spread or variability of the scores allows you to make a much more informed decision. Footnote to this story. We learned through experience that it is best to look at more than a single variable, temperature, when planning a vacation, as it rained on every day throughout our vacation. However, we still had a good time because it was warm. Another example where variability of scores can have a big impact is this display, which presents the distribution of hourly production of 2 computer plants. The top one is in Canada and the bottom one is in Waterloo. Both plants have the same hourly average production of 50 units per hour. However, production output of the Waterloo plant is far more variable. 30% of the time, the Waterloo plant's production is faster than Canada, but 30% of the time it is also slower. Now, if this was your company and you had a super important client that ordered computers from you and they wanted to know precisely when the order would be filled, which plant would you send the order to? It would likely be Canada, as the production speed is less variable and more predictable. By now you should be beginning to understand the importance of variability in the properties of a set of data. Central tendency alone is not enough to describe a data set. If you were hiking through the woods and you came across a stream you had to cross, and all you knew that the average depth was 1 meter, would that be enough information to allay any concerns you might have about crossing the stream? It shouldn't, because all you know is the average depth. You could take a step into the stream, it could be ankle deep. 3 steps further, it could be over your head. Knowing the range of water depth would be much more helpful for you as you're crossing a stream. The second point is, in order to observe differences between groups, only knowing measures of central tendency between the two groups is not enough. It's important to also know their spread, to see the degree to which the two distributions might overlap. And third, variability can serve as an indicator of skilled performance level. Best example I have of this is golf. I'm not a very good golfer, but sometimes I get lucky. I occasionally have a hole where I come close to par. But most of the time, I'm not so lucky, and my scores vary tremendously, usually very high. Now contrast that to a professional golfer whose scores are always around par, slightly below or slightly above. They don't vary as much as a hack golfer like myself. We are going to look at 3 main measures of variability: the range, variance, and standard deviation. Let's begin with the range. It's the simplest and easiest to conceptualize measure of variability. All it is the highest minus the lowest score, and that's range. To determine this, we look for the highest score in the data set, we look for the lowest score, and then we subtract the lowest from the highest. Though the range is simply the difference between the largest and smallest value in the data set, there are some properties of the range that are important to highlight. First of all, of course, only 2 values in the data set are used in its calculation, and therefore it's influenced by extreme values, and the range can be a rather unstable measure. Though it is easy to compute and definitely easy to understand, and it's often used for general descriptive purposes. In fact, the range serves as an effective descriptor of our 2 computer production plants. At Canada, the production is as high as 52 and as low as 48. That's a range of 4. Whereas at Waterloo, production is as high as 60 and as low as 40, and that's a range of 20. In this case, range does accurately capture the difference between these 2 plants. But in most situations, the range does not provide an accurate reflection of variability in a data set. Take, for instance, this example. Here we have 2 extremes at 1 and 7, yet all the other values in this data range between 3 and 5. So here's the challenge. Can we come up with a measure that takes variability of all scores into consideration? Kind of like the way the mean works, where all values of the data set are used to calculate the mean. Would deviation from the mean work as a measure of variability? Recall what I mean by deviation from the mean. Remember our small data set from 1 to 5? We first calculated the mean, and as you recall, the formula for the mean requires us to sum the values of x, which equals 15, and the number of observations is 5. Then, of course, the formula for the mean is the sum of x over the n, which is 15 over 5, and that equals 3. With the value of the mean now, we can figure out the deviation from the mean for each score in our data set. Here's the formula once again for that. And when we do this, as you recall, when we calculate the deviations, sum them up, they equal 0. So it would make good sense to come up with a measure of variability that takes all scores into consideration, and using deviation from the mean would be an excellent measure, except for the fact it will always sum to 0. So how can we overcome this problem? One possibility might be to use absolute values of the deviation. Absolute values are symbolized by vertical lines on either side of the equation or function, and all they are is the removal of any negatives that might appear. Therefore, the -2 changes to 2, -1 to 1, and when we sum this up, it doesn't sum to 0, it sums to 6. However, most of you have probably never even heard of absolute values. Nowadays, they are rarely used in mathematics, possibly because there are simpler ways to convert negative values in datasets. The alternative is squaring each deviation. Let's see how this works. We'll begin by writing the formula for the deviations from the mean squared, and then we'll calculate the deviation squared for each observation in our data set. We will then sum them up. They sum to 10. And there we go. We have a way to calculate variability using each value in the data set without it summing to 0. So the solution is the sum squared deviation from the mean. And then, if we want to calculate the average amount of variability, all we have to do is divide this sum squared deviation from the mean by n. And this average variability is also known as variance. Once again, we calculate variance by subtracting the mean from each score, square every deviation from the mean, sum the squared deviations, then divide the sum of squares by n, and that is variance. Using our simple numeric example, we've already calculated the sum deviation from the mean is 10. Then we're going to divide that by n, which is 5, which equals 2. So variance equals 2. So variance is the average squared deviation from the mean. That's not only a mouthful to say, it's also quite difficult to interpret, because our measure of variance has been transformed into squared units. It would be a whole lot easier if our measure of variance was in the same units as our original data set. So, in order to transform our variability measure back into its original units, all we need to do is take the square root of variance to get rid of the squared values. And we call this measure standard deviation. It's the typical amount that scores vary or deviate from the mean. In our simple numeric example, once again, we can calculate the standard deviation by taking the square root of variance, which is the square root of the sum squared deviations from the mean, divided by n, which would be 10 square root of 10 divided by 5, which equals the square root of 2. And the square root of 2 equals a value of 1.41, and 1.41 is our standard deviation. An additional key point about variance and standard deviation is that we need to distinguish between variances and standard deviations that are drawn from samples and those that represent entire populations. The symbols for samples are the letters s squared for variance and s for standard deviation. For populations, we use the Greek letters small sigma that looks like an O with baseball cap on. Small sigma squared is for variance, and small sigma is for standard deviation. Notice that we also have changed the symbol for mean when it comes to the population. We use the Greek letter mu, which looks like a U with tails extended on either end. Finally, statisticians have determined that the formula for variance and standard deviation slightly underestimates variance and standard deviations in the population. Therefore, whenever we calculate a sample, we perform a correction by changing the denominator to n-1. Now that you've learned all about what the range, variance, and standard deviation are, here's your chance to take the sample of data and calculate all three measures. Please pause the video now and do the calculations, and then resume the video to check your answers. And here are the answers for the range, the variance, and the standard deviation. Did you get them correct? If not, look back at how the calculations were derived and review this video once again. So the fun thing I want to show you in today's video is how to actually calculate variance and standard deviation using Excel. I've copied the sample data that we used for in the last exercise here into this data set, and it is in column A here. You can see the same values. They should look familiar to you there. Now, I'm going to show you two ways to calculate variance and standard deviation, and mean for that matter. The manual way, and also using the functions that Excel provides you with. Now, along with the data that I've included in this worksheet, I've also included some labels of key measures that we'll have to calculate here. You'll notice that we've got the deviation from the mean, the deviation from the mean squared, sum, n, mean, and the variance for the sample and standard deviation for the sample, all labeled here, ready for me to fill in the values that we will need. So let me start with actually calculating the mean. Now, of course, the mean requires us to sum the values of x, so that will be our first step here. And the way in which we're going to do that is we're going to use the sum command up at the top of the screen here. And when we click on it, it does highlight cells with numbers on it in close proximity to the cell that we actually were calculating the sum to. So we have to adjust that and highlight the numbers that we want to be summed up. We do that, and it comes out to a value of 48 once we press enter. Now we need to actually calculate out or add up the number of observations in the data set. We can manually do that, but we can also use the COUNTIF command here to do this. This is COUNTIF. We want to give the range of scores. That will be column A. And then we want to give the criteria. Now the criteria is going to be values greater than 0. And so we're going to use a double quotation mark, greater than sign, 0, another double quotation mark, and then that with the end bracket, and that will sum up our values, and our n is 8. Now we're able to calculate the mean. The mean is the sum of x divided by n, so we can actually click on the cell with this sum on it, divided by the cell with the value for n. And that would give us a mean of 6. Now we could do the same calculations using the mean function in Excel, and we can find that by going to the sum icon and click on average, highlight the scores that we want to be averaged, and that will provide us with the same value. Now, moving forward, we can now take the deviation of each score from the mean. Now, and the equation would be equals the value of x minus the mean. Now, of course, we need to change that to an absolute cell reference by putting the dollar signs in. Once we do that, we can use the cell reference to actually figure out the deviations from the mean for each value, and sliding that down like this. Next, we need to calculate the square deviations. We use the formula equals the deviations from the mean to the power of 2. That would be the caret sign, which is shift 6 with the value 2 in there. That will square each of the scores. We use the file handle to slide it down to calculate all the numbers. Next thing we'll want to do is take the sum of the square deviations by using the sum sign, and that will equal 18. Now we're ready to calculate our variance. Now that's the sum square deviation from the mean, which is 18. We'll just click on that cell, divided by, this is going to bracket, the n minus 1, because we're using a sample here. And that comes out to that value there, 2.5. You can probably just round that to 2 decimal places there. Next is to calculate the standard deviation, which we use the square root command. That's SQRT bracket. Click on the cell with the variance in there, and that will give you our value for standard deviation. Excel also has variance and standard deviations built-in functions as well. To find them, go to the function icon beside the formula bar, and you can search. You can actually search up above here for the words standard deviation, or what we will be actually searching first is for variance. Now, when you do that, once you type in the word variance, you can press the go button. It will search out all the different types of variances that Excel has. We want to use var.s, which is for the variance for the sample. When prompted, you'll want to highlight the range of scores that you'll want to include as your variance there. And as you can see, you get the same value as we did when we worked it out manually. Same goes for standard deviation. You can search for standard deviation and then press go. You can see that there's 2 main types of standard deviations that we'll use. That would be standdev.s for sample and standdev.p for population. Highlight the cells that you want in your standard deviation, click OK, and there you go. And that's the exact same value for standard deviation as you calculated manually. You'll be using these Excel commands when you do your assignment number 2. And that's it for this lecture. Look for the assignment number 2 in DC Connect, and I'll see you next week. Bye for now.